We're continuing to talk about UART protocol, and we're going to talk right here about how synchronization happens. So the transmitter and the receiver, they have to be synchronized. That is, the receiver has to know when to expect data from the transmitter. And it has to be fairly accurate about the timing that it expects. And UART is an asynchronous protocol, meaning it has no clock. Normally, if you have a synchronous protocol, the clock is how it's synchronized. When it sees the rising edge, it knows data will be sent. But this doesn't have a clock. So it has to figure out when data is going to be sent another way. So UART synchronization, the reason why it's important is, so what it means is that the receiver has to know when it's looking at the value on that wire, on that serial wire, it has to know which bit it's reading, if it's supposed to read and what bit it's reading. It has to count the bits. So for instance, say it knows that you're sending 8 bits. It has to know, okay, now is when I should sample bit number 1, and then now is when bit number 2 should happen, now is when bit number 3 should happen, and so on. So it has to know when to expect each bit to arrive. So it knows when to sample the signal on that wire to get a 1 or a 0. If it gets out of sync like that, that's synchronized. If the receiver knows when to expect each bit sent from the transmitter. If it's not synchronized properly, then the receiver will not expect the bits at the right time. It'll receive the wrong data. So here's an example. Right here, we're showing a little timing diagram, and we're really showing 3 bits being sent. Okay? There's a 1, there's a 0, and then there's a stop bit. That's what should be sent. Okay? That's what the transmitter is actually sending. And the stop bit is high. Right? The stop bit is at the end where the signal is actually high. So it should be sending a 1, then a 0, then a stop bit. These are just the last bits of the communication. So I'm just showing bits 7 and 8 of the last 2 bits of, say, an 8-bit set of data. And then after the last 2 bits, you're going to expect the stop bits. So what should be, the expected bits as they are correctly observed would be, bit 7 would be a 1, bit 8 would be a 0, and then the stop bit is the next bit, and the signal is high. And it would say, oh, okay, this is a stop. And if that happened, if the receiver correctly knew when to observe those signals, it would receive the correct bits. It would receive a 1 for bit 7, a 0 for bit 8, and then it would receive high at the stop bit, and that means that it's working. That means that is correct. That is a correct assumption. If the stop bit has to be high. If the stop bit is low, then there's a problem with the communication. So if the receiver knows exactly when to sample the signals, it will receive the right bits. But let's say the receiver is off. Okay, it is not synchronized properly. It started sampling earlier, too early, right? So if it started sampling too early, it might sample the values at the wrong time. So when that 1 comes through, instead of thinking, oh, this is bit 7, it might think it's already on bit 8. And if that were the case, then when that 0 comes through, instead of thinking that it's bit 8, it would think that that was the stop bit, since it's the one after bit 8. And then it would read a 0 for the stop bit, and that would cause a failure, because the stop bit has to be 1. So if it was not synchronized right, then it could read a 0 for the stop bit. That would cause a failure, and it would lose the whole byte, and the byte would have to be resent. So what I'm saying here is that the receiver has to be synchronized with the transmitter. It has to know when the transmitter is going to send a bit, and it has to know which bit is being sent. So it needs to synchronize on the beginning of the communication. So that's what the start bit is for. So imprecise communication, imprecise start time, if it gets the start time wrong, then it can it'll receive the wrong bits and maybe fail in its communication. So the start bit is how synchronization happens. So the start bit, remember at the beginning, before you've actually started sending anything, the wire is high, right? The single wire is going to be high. And the receiver knows that transmission is going to start, the start bit is happening, when it goes from high to low. So when there's a falling edge on that signal, then it says, okay, this is the start bit. And now is when I have to start synchronizing myself. Now, we got 2 examples, 2 pictures up here, 2 slight timing diagrams. And what they're showing is 2 different situations. Now, remember that this UART, it was made a long time ago, and it's made to be robust in the face of noise. So noise, you get all kinds of electromagnetic noise on these signals. So this signal, maybe it's supposed to be high because you're not communicating. But there's some kind of a glitch, some kind of noise, electromagnetic noise, which forces the signal to go low mistakenly. Okay? Now, when that happens, if the receiver is too quick, it might say, oh, the signal went low, I guess a communication is starting. But maybe it's just a glitch, a temporary bounce down, right? And it shouldn't consider that to be a real signal, right? It should ignore a short glitch. So what happens is, it's got to measure the time that the signal is low. So on the left, it's just a glitch. The signal goes low, but for a very short time. If it's too short, then the receiver should say, oh, that's not real, that's not really a start. But on the other hand, on the right, if this signal goes low and stays low for a significant amount of time, then the receiver should say, oh, this is a real start, I need to synchronize myself. Okay? So the receiver has to be able to distinguish between a glitch for a start, which is not a real start signal, and a real start. So it has to count how long it stays low. Now, see those little up arrows on the timing diagrams? Those are the sampling points. Those are the points in time where the receiver is checking the signal value. And you'll notice, like with the glitch, it goes low for only 3 sample points. So the receiver would say, oh, it's or rather low for 3 sample points. That's not enough. Where if you look at the one where the start bit is detected, the one on the right, it's low for, I don't know, 8 sample points. And it would say, okay, that's sufficient. So that's what's going to happen on the receiver end. It's going to sample over and over, faster than the baud rate, typically 16 times faster at least. And it's going to count how many times to find the start bit, it's going to count how many samples it's low for. If it's low for enough samples, then it says, yes, that is a real start. So detection of start bit is used to synchronize the receiver and the transmitter. It synchronizes based on the falling edge of the signal, and it recognizes the start bit based on the falling edge. The following 0 must be of sufficiently long duration to screen out any kind of noise. The receiver has to sample faster than the baud rate, typically 16 times faster. That's common. The start bit is indicated by a 0 for at least half a period. So the length of the period depends on your baud rate, but let's say we were using a baud rate of 9600 baud, right? If you remember, the period length for that is 104 microseconds. So the whole period is 104 microseconds. Half a period would be 52 microseconds. So the receiver, if it sees that signal go down low for 52 microseconds, then it says, okay, this is a real start signal. We really started communication. I need to synchronize myself now against that falling edge. Where if it's less than 52 microseconds, then it says, oh, that's just a glitch. I can ignore that.